In this third part, we're going to look at binary arithmetic operations and conversions. So we're going to look at how to do multiple bit additions, multiple bit subtractions, multiplication between two binary numbers, and more about conversions between binary and decimal, and other types of conversions such as octal or hexadecimal to binary or to decimal. So the binary addition is quite a simple case, the idea being that you add the two digits together. If they add up to greater than 1, then you have a carry. Carry is 1, similar to a decimal type addition. In this case, we would have 1 plus 0 with 0 carry. Also notice that this 0 here that's underlined always has to be added there as default. It's kind of the carry in. And then after that, we simply add the values together, all three of them, and then if we need to carry, we add the carry. So add 1 0 0 gives you 1, 0 0 gives 0, 1 0 gives 1, 1 0 gives 1, 0 1 gives 1. So this is the sum, very simple case. So let's look at this second case where we're going to actually need to do some carry. So once again, we've got this 0 placed up here as the default carry in, and 1 plus all of these zeros is 1. Now 1 plus 1 giving 2, but since this is binary, then the maximum value you can have is 1 before you actually carry over. So we're going to put a 0 here from the previous carryover, and we're going to put a 1 here. 1 plus 1 being essentially 10. So put a 0 there and carry the 1. Now we add these three together. 1 plus 1 plus 1 is 3, or in binary 3 is 1 1 1. Just to show you that, we'll say we'll count in binary. We go from 0 0 to 0 1 to 1 0 and 1 1. So this being 0 in decimal, this would be decimal. This is binary, this would be 1, this would be 2, this would be 3. So 1 plus 1 plus 1 giving 3, giving 1 1. So 1 here, and carry the 1. 1 plus 0 is 1. 1 plus 1 is 2, which is the same as 1 0. 0 here and 1 there. For subtraction, we can approach this in a similar way to what we would for decimal type of subtraction. We have a minus end and we have a subtract end. The minus end is, say, the initial value, and the subtract end is the thing we're taking away, and the difference is obviously the difference between those two. So in this case, we've still added a 0 here, but we're not calling this the carry in, we're calling this the borrow in, and in this case it's what's available from the least significant bit. So we say that if the subtract end is greater than the minus end, we have to interchange and append a minus to the result. If the subtract end that we're looking at, for example this one, if this was greater than this one, then we'd have to borrow in from the minus end with the digit further down, a more significant digit. In this case we won't need to do that because it's a simple example. So we can have 0 minus 0 giving 0, 1 minus 1 giving 0, 1 minus 0 giving 1, 0 minus 0 giving 0, and 1 minus 0 giving 0. So the difference between these two values is 1 0 0. So in this case it's a slightly more difficult example. We're going to have to use the borrow in. So we have 0 minus 1. We can't do that. So we can borrow in from here, and we can have 2 minus 1 giving 1, 0 minus 1, we can't do that, so we can borrow in. We can have 2 minus 1 giving 1, 0 minus 0, 0, 0 minus 0, 0, 1 minus 1, 0. So the difference between them is 3. So for binary multiplication, it's simple. It's the same as what you'd be familiar with. 0 multiplied by 0 giving 0, 1 multiplied by 0 giving 0, 0 multiplied by 1 giving 0, and 1 multiplied by 1 giving 1. So if we extend that multiplication into multiple digits, we have the multiplicand on the top and the multiplier underneath, and then we use partial products in order to work out the products for each of the digits of the multiplier, and then we're going to simply add them together to give what we're going to call the product. So for example, we will multiply 1 by each of these in order to give this row, and 0 by each of these to give this next row, and then 1 by each of these to give the last row. Notice the same as normal multiplication. Every time you go to the next digit of the multiplier, you simply shift this way, however many digits it is. So for the 0th one, it's a 0 shift. For the first one, it's a 1 shift. For the second one, it's 2 shifts. So each of these, you could read them as zeros. You can write zeros if you want. You could leave them blank, but it might be easier to fill it in with something so that at least these columns will line up. So when you do add up 1 plus something, you should get 1 here. So these should be read as zeros. Again, 1 plus 0 plus 0, 0 plus 0 plus 1, 1 plus 0 plus 1. We've got a carry here. 1 plus 0 plus 0 is 1, and 1 plus nothing is 1. So there's our product. These are some useful base conversions that you might want to memorize. Certainly the first few are down to 8 bits, knowing that that's 256, maybe 10 bits because that's your kilo reference, essentially 1000, so kilo. This is essentially 1 million, so mega, and then of course you can work all of these out. So in order to convert from binary to decimal, we already did talk about this earlier when we were talking about the radix example. So we can use the decimal arithmetic, form the s digits times the respective power of 2. There's another way of writing the radix being 2 to the power of whatever, wherever it falls. So let's do a couple more examples here. We're converting this binary value into a decimal value, the radix 10, and we're going to do the same as what we did before. Let's write the index here. If we had a radix point here, this would be the 0th, 1st, 2nd, 3rd, 4th. And so we use 2 to the power of 0, but let's leave out the zeros this time. We don't need to worry about this one or this one. We'll just do 1 times 2 to the 1 plus 1 times 2 to the 3 plus 1 times 2 to the 4, giving 2 plus 8 plus 16 equaling to 26. For this second example, we want to convert this decimal number, 625, to a binary number. In order to do that, it's useful to look at this table that was shown before and find out which values you need to add up in order to get to this 625. So obviously we're not going to need 2 to the 10 because 1024 is larger, but we're going to need a 512. So if we write all of these out, then we can work out which ones need to be added up in order to get to that 625. So definitely we need a 512. 625 minus 512, and we get 113. We don't need this one. We don't need 128, but we're going to need a 64. It's 49. So we're also going to need a 32. 17. So we're going to need a 16. And we don't need an 8. We don't need a 4. We don't need a 2, but we need this 1 as well. So what we've needed is, by looking at the previous page, we've needed 2 to the 9 plus 2 to the 6, 2 to the 5, plus 2 to the 4, plus 2 to the 0. Therefore, we have a binary number of a 1 in the 10th across. So 1, if we wrote this index. So we've got a 1 in the index 9, a 1 in the index 6, a 1 index 5, a 1 in the index 4, 0, 0, 0, and then a 1 in the index 0. So then this is our binary number. Here are some commonly occurring bases. We've obviously already seen binary and decimal. We've already had a look at these ones, where the radix is 2 and 10 respectively. Obviously the digits being 0 and 1, and then the digits being from 0 to 9 to make up the decimal. Octal, like octagon or octopus, this is 8, so it means there are 8 digits from 0 to 7, so this has a radix of 8. And then another one which you may be familiar with is hexadecimal. Hex being 6, like hexagon, has 6 sides, and decimal being 10, so 16. And this is the digits from 0 to 9, and then A, B, C, D, E, F. So in terms of hexadecimal, let's have a think about what the 6 letters after the 9, so that is after this digit here, what do these actually represent if you were to be counting in decimal? So count from 0 to 9 and then keep on counting. So obviously the 6 letters after the first 10 digits, after the first 10 integers in the hexadecimal represent the decimal numbers 10, 11, 12, 13, 14, 15. And then of course when you get to the 16, then you'd be counting 1, 0. which is why we can't use 10, obviously, but actually 10 in hexadecimal can be represented as 10 with the radix 16 down the bottom, and then in decimal that number would be after 15. What's the next number? 16. So 16 in decimal. And we can see that by saying this is actually 1 times 16 to the power of 1. This is 0 times 16 to the power of 0 because of the index. So here are the numbers for the different bases from decimal 0 through to decimal 16, and then binary and octal and hexadecimal. So we already said that we can go between 0 and 16, and that would equal the numbers from 00 through to 10 in hexadecimal. In octal, when we're counting just to 8, then you can see that would be 20, like 20 in octal. We've counted first to 7, and then when we get to the 8th value, then we've actually got a 1 in the 8's column and a 0 in the 1's column. And we count up again to 8, and when we get there, we've got a 2 and 0. And then in binary, obviously just counting like the normal way. Might be good to memorize these, or at least know how to get to these answers very quickly. So we did a little bit before about converting between the integers with fraction parts in them, between numbers with different radixes, and we showed an example of converting between the binary number and the decimal number. So a way to generalize this is to think about repeatedly dividing the number by the new radix and then saving the remainders and then continuing to divide that. So the digits for the new radix will be the remainders in reverse order of their computation. If the new radix is greater than 10, such as in hexadecimal, then we can convert all the remainders to be greater than 10. But we obviously don't use 10, 11, 12, 13, 14, 15 for hexadecimal. We'll use A, B, C, D, E, F. And then to convert the fraction part, we repeatedly multiply the fraction by the new radix and save the resulting integer digits. And the digits for the new radix are the integer digits in order of their computation. And then in the same way, for the hexadecimal case, if the new radix is greater than 10, then we convert all the integers to be greater than 10 and we use the digits A, B, C, D, E, F. Okay, so for this next example, we're going to be converting it using our new method. So we've obviously already converted between decimal and binary before, but we're going to use the generalized method to convert 46.6875 in decimal to binary, or base 2. So we're going to break it up into the 2, into the integer part, into the fraction part, and we're going to convert 46 first of all using the divide and remainder method. So let's write 46 divided by 2 equals to 23 with a remainder of 0. 23 divided by 2 equals 11 with a remainder of 1. 11 divided by 2 equals 5 with a remainder of 1. We continue on in this way, and I've sped up the writing. Okay, so now we're going to write these binary digits in reverse order, with this being the first one. So we write out 1, 0, 1, 1, 1, 0. So that should be the answer, 46. However, let's just check to make sure. So we've got 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 1 times 2 to the 3 plus 0 times 2 to the 4 plus 1 times 2 to the 5. This is 0, 2, 4, 8, 0, 32, 46. Okay, so that's good. Now we're going to convert the second part by using the multiply method. Multiply method, we will continue to multiply by 2 until we get the value of 1. That's what we're looking for, 1.00000. And each time we do the multiplication, if we get an integer, then we write that down. If we don't, we write down 0. So let's start with 0.6875 multiplied by 2 equals 1.3750. And so we have an integer part of that of 1. Now we just do the remaining part. So we're interested in this part, fraction part, 0.375 multiplied by 2 equals 0.750. And the integer part of that is 0. So once again, multiplying the fraction part, 0.75 by 2 gives 1.5. Integer part of that is 1. The remaining fraction part, 0.5 multiplied by 2, gives 1.0000000. Integer part of that is 1. So we now write that in this order, going down rather than up. In the previous case, we started at the bottom and we wrote these digits down as most significant to least significant. In this case, we're going to do the opposite way around. So we're going to write down that after the radix point, 1, 0, 1, 1. So we can check that. 0.5 plus 0.125 plus 0.0625 equals 0.6875, which is good. That's what we want. So we join the results together. First of all, this result. Second of all, this result after the decimal place. Then we can say that 46.6875 equals 10111, radix point 1011 in base 2. So as I said, it's always a good idea to check the conversion, make sure you can convert it back. And obviously to convert back, we once again sum their digits multiplied by the respective powers of r, but I'll leave it to you to look at that a bit more closely. In the case of converting from octal or hexadecimal, so read these brackets for this slide as or, to binary and then back again. When we go from octal to binary, we have to restate the octal value as 3 binary digits, starting at the radix point and going back both ways. Notice this is for the octal case to binary. So this is octal to binary. Notice how we've got these groupings here, and they're grouped into 3 digits, 3 binary digits. In this case, it's 110, this is 111, 011, then after the radix point. Again, we see this grouping. So these correspond directly to the number in that place. So notice how this is kind of grouping 1, grouping 2, grouping 3, and this is 1, 2, and 3. So we want this value has to equal the 3, this value has to equal 7, this value has to equal 6, and then to the right, this value has to equal 1, this value has to equal 2. Then we don't leave it with these gaps here, we just write it all together. So this is the way you would write that binary number all together. In the case where we want to do a binary to octal, so that's the opposite way around, or to hexadecimal, we group the binary digits into 3s or 4s if it's hexadecimal, starting at the radix point and going both ways, and then pad with zeros on either side to make it so that we always get the groups of 3 or 4 depending upon if we're converting to octal or hexadecimal. And then we convert each of these groups in the same way here we converted each of these digits, these octal digits, to groups of binary digits. Now in this case we're going to convert each of the groups into a single octal digit. So we've got this group here equaling 2, so this is this one. We'll write these numbers above here, so this is going to be 2, match with that. So we put all those numbers together and we get the octal equivalent of this binary number. So just so that we don't have to read it as octal or hexadecimal, I've written this slide which is the same case but for hexadecimal to binary and back again. So in this case, instead of grouping in 3s like we did for octal, we're going to group into 4s. So we're going to restate it as a 4-digit binary number and then go back and go both ways from the radix point again. So notice this grouping here, and we're going to convert it. This one is 6. This one is 7. So writing all those together would give you 673.12 in hexadecimal. This is the binary equivalent. I've written on a new line to make it a bit clearer, but instead of having these spaces in between, we've removed the spaces, just one long binary number. And then in the second case, we're going to convert from binary back to hexadecimal, and we're going to be grouping in 4-bit groups, and we go both ways from the radix point again. And importantly, make sure we pad with zeros in the fraction part if necessary. So in this case, if we were to write this normally, we usually wouldn't write this extra 0 on the end. But in the case where we want to do the binary to hexadecimal conversion so that we get these nice 4-bit groups, then we're going to make sure that we have this 0 on the end here. So you can see these groupings here, read X point here, and then we convert each one of these individually. And notice if you hadn't put that extra 0 on the end, you may have mistakenly converted this to a 3, which is not correct. It needs to be a 6. And so this 26153 read X point 7406.